So what we will do is, again, we will define the sum random variable, but then we will divide it by the number of repeated experiments. So what we are doing is effectively we are computing an average of the outcomes. So x1 through xn are independent samples or observations or measurements, depending on what the random experiment is, of distribution x. Okay, we would like to estimate the mean of x. We do not know it. We do not know the distribution, so we do not know the mean, but we can repeatedly observe an outcome. Okay, like the die, you can throw it again and again and again and record the outcomes. Those will constitute the x's. And we will define the sample mean as this: the sum random variable divided by n. So it's simply an average. Okay, nothing very fancy here. It's just the average of the outcomes. How would you compute the mean of a sequence? You don't know the distribution. You just have the sequence. It's data. Okay, you just add them all up, divide by n, the number of observations. So that's your average. That we call the sample mean. Now what you need to observe here is the sample mean is also a random variable. Why? Because it's a function. It's defined as a function of random variables. So it's when you look at a set of data, you have a set of numbers, you add them all up, divide by n, you get a number. Okay, but that's the sample mean of one data set. What we are doing here is generalizing this approach and investigating the properties of the sample mean. And for that, the sample mean in this setting itself is a random variable because it is defined as a function of random variables. Okay? So it's a random variable, and we can write its expected value of m sub n. Just plug in the definition of m sub n, which is equal to 1 over n times s sub n. Okay, 1 over n is just a constant, can take it out of the expectation. And then I have the expected value of s sub n, which I know to be n times the expected value of x. Okay, so this is the sum of random variables, s sub n, and we know the random variables to be IID. Therefore, the expected value of s sub n is n times the mean of x. Divide by n, the n disappears. You get the expected value of x. So the result is the expected value of the sample mean is in fact equal to the true mean, mu, of random variable x, which we didn't know. Okay? In this case, we say that the sample mean is an unbiased estimator for mu. Now, you have to understand one thing here. If you have a data set, what I'm saying here is not that when you take the average of the data set, you will definitely find the real true mean. That's not what I'm saying. Because recall what I have said here. Sample mean itself is a random variable. I'm talking about not its value, not its outcome. I'm talking about its expected value. Okay? The expected value of the sample mean is equal to the true mean. Okay? That's a very important distinction. You have to understand what it entails. When you have a data set, when you take the average, what you will find is not guaranteed to be the true mean. It's a realization of the random variable sample mean. Okay? But if you do that long enough, what I'm saying is you will approach to the true mean. Now, we have seen that the mean of sample mean is in fact equal to the true mean, but it is still a random variable, as I've said. But we will look at its variance. Why? Because its variance, as you will see, it will depend on n. Okay? So that will tell us something about the convergence of the sample mean to the true mean. So when you look at the variance, again, just put in the definition, sample mean minus its mean, this is the mean of the sample mean, okay, square expected value, this is the definition of variance, nothing else. And here, just put in the definition of m sub n as 1 over n times s sub n, and this mean here as the expectation of 1 over n times s sub n, just the definition of sample mean. But you see, this is in fact the variance of 1 over n s times n. Okay, again, there is nothing new. As we know, 1 over n s sub n is by definition equal to m sub n. Therefore, since 1 over n is a constant, it comes out of the variance as 1 over n squared times variance s sub n. Variance of s sub n, I know to be, is the variance of the sum of IID random variables. Therefore, it is equal to n times the variance of x, as we have derived earlier. Okay, so n times variance of x divided by n squared, which comes from here. What you get is the variance of the sample mean is equal to the variance of x divided by n. The key observation here is, provided that the variance of random variable x is finite, the limit of this expression goes to 0 when n approaches infinity. So what does this tell us? The sample mean, m sub n, is still random. It's a random variable. But if the number n increases, it goes to infinity, it increases, the variance of the sample mean decreases. It approaches 0. Okay? So what's a random variable with a variance of 0? It's not random. It's deterministic. So what we see here is that the sample mean at the limit as n goes to infinity converges to the true mean. It becomes deterministic at the limit. Okay? So this is a very important result. Sample mean, as the number of samples increase, approaches, converges on the true mean. And you see the convergence of, the rate of convergence here is 1 over n. Okay, it's linear in the number of samples.